Section 2.1 deals with quadratic functions. These are functions that look like this if they're written in standard form. F of x equals ax squared plus bx plus c. So I've got three potential types of terms. I can have some x squareds, some x's, and a number. The one rule that I'm going to have is that a cannot be 0. In order to count as quadratic, I actually have to have some x squareds. If I didn't have any, I'd have just a linear function. If I didn't have any x's either, I'd have just a constant function. Okay, so it's perfectly okay if b is 0 or c is 0, but I've got to at least have some x squareds. Okay. Now, this is standard form. Any quadratic function can also be written in what your book calls vertex form. I often refer to this as grapher-friendly form because it's easy to graph it if it's given in this form, and that's because I can see this is just going to be some transformation of the squaring function. Okay. So I know that the graph is going to equal a parabola. We're just transforming it in some way, shape, or form, and I can pick out what the vertex is because I can see I'm subtracting h before I square things. So that's going to be a horizontal shift. Okay. And I'm adding k after I square things, and that's going to be a vertical shift. So the vertex will be hk. Now do be very careful. This sign matches whatever this sign is. This sign is the opposite of whatever this sign is. Okay, so what I want to do is just review graphing something in vertex form. And then once we've got the graph, we'll ask a few questions about that graph that incorporate some of the other concepts that we talked about in chapter 1. So let's just say f of x is equal to -2 times x minus 2 squared. Oh, let's actually make that x plus 2 squared plus 4. Okay, now if I were to graph this just using the transformations that we've done in the past, I would say, okay, let's create our table of values, or not our table of values, our table where we list what we would do in evaluating the function and then the corresponding transformation. I'm going to go ahead and work through that and then just point out some shortcuts that we have in this particular case. So if I were plugging in a number for x, the first thing I would do is I would add 2. Then I would square that result. Now squaring, that's my parent function. After I've squared, I would multiply by -2. And then the last thing we would do is add 4. Now remember, anything we do before the parent function affects the graph horizontally, and anything we do after the parent function affects the graph vertically. So adding 2 before we square is going to shift things to the left 2. Multiplying by -2 after we square will do 2 things. That's going to be a vertical flip and a stretch by a factor of 2. And then adding 4 is a vertical shift up 4. So if I were to graph this by just doing these transformations one at a time, here's my basic parent function, and I've usually been asking you to keep track of 2 points. The vertex is, of course, incredibly important, and I've usually asked you to include the point whose x value is 1, so the point 1, 1, just because that helps me to keep the steepness correct. This is sort of a moderate parabola. Some parabolas we get are really tall and skinny, and others are really short and fat, and by plotting one additional point, that helps me to keep track of that. Okay, so it does not matter whether I do my horizontal or my vertical transformations first. I'm going to just do the horizontal one first. So if I were to shift things to the left 2, my vertex moves to -2, 0, and this point 1, 1 moves to -1, 1. So all I'm doing is the opposite of adding 2. I'm subtracting 2 from my x values. All right, and then for the vertical transformations, remember we always move away from the parent function, so I'm doing these in the same order in which they appear on this table. So if I were to multiply by -2, that's going to do two things. It's going to flip it, and it's going to stretch it vertically by 2. So I accomplish those things by multiplying my y values by -2. So -2, 0 doesn't change at all. But -1, 1 becomes the point 1, -2. And so I can see now it's opening upside down, and it's skinnier than it was. Okay. And then we're supposed to shift things up 4, which we accomplish by adding 4 to our y values. So the vertex is now going to be at -2, 4. And this point gets moved to 1, 2. Sorry, -1, 2. All right, excellent. So we've got our parabola opening upside down, steeper than the parent function that we started with. Okay, now I did that by graphing the transformations one at a time. And I think it's important for us to understand that, but particularly when it's a quadratic function, and so it's a parent graph that we're very, very familiar with, or at least we should be by the end of the semester, there are some nice shortcuts. Okay. So basically, to graph a parabola, I need to have the vertex, and I need to know whether it opens up or down, and have one other point to really help me to make sure that I get the right approximate steepness. I can actually get all of that from here. Okay. So notice the vertex ended up being -2, 4. That's because we shifted things 2 to the left and up 4. So if I just look at the horizontal and vertical shifts, I can pick out the coordinates of the vertex directly from the formula when it's in vertex form. I know it's going to open down because in multiplying by -2, that accomplished a vertical flip. I also know I've stretched things by a factor of 2. Okay. So I could actually get this point fairly quickly, because notice with the parent graph, if we go over 1, we go up 1 to get to this second point that was helping us determine how steep or not steep to make the graph. If I'm stretching that by a factor of -2, instead of going up 1, we're going to be going down. And instead of it being 1, it's going to be 2. So I can, from here, just say if I went over 1, I'd have to go down 2. Because I've stretched that vertical distance by a factor of 2 and flipped it. Okay. So I can get that second point right there of -1, 2. So I can go ahead and sketch my parabola without having to do things one at a time. That's kind of nice. Okay. So if you're comfortable doing that, that's fine. If you prefer to do the transformations one at a time, if that makes you feel more comfortable, I'm totally fine with that. Okay. Now, as we worked through chapter 1, we talked about some other points that we might be concerned about, including intercepts. So if I wanted to get the y-intercept and the x-intercept, or septs, sometimes there's more than one of them, okay, I can do that. Remember, the y-intercept is going to be where we're on the x-axis. So that means that x is going to be 0, and I just need to know the y value, which I'll get by plugging in 0. So let's just do that. F of 0 is -2 times 0 plus 2 squared plus 4. This becomes 2 squared, which is 4, so that's -2 times 4 plus 4. That's -8 plus 4. That's -4. So my y-intercept is at 0, -4. Now I could sort of see from the graph that we were going to cross somewhere down here. Now I actually know a little bit more precisely we're crossing at 0, -4. Notice, if I have that, I don't really need that point, because knowing that the vertex is here and I've got to pass through this point is going to help me get about the right steepness. So if I have the vertex and a second point, I can approximate the right steepness for my parabola, and sometimes I may get a second point by plotting the intercepts instead. So it's not always going to be necessary. When we were doing transformations, I said, keep track of where that point 1, 1 gets mapped to, because I wasn't asking you to keep track of any other points. But if you're asked to get the intercept, very often they can do the same job that this point was doing, which is tell me how steep to be. And then they do another job. They also tell me where our graph crosses the axis. All right, to get the x-intercepts. Now, we will encounter some parabolas that don't have any x-intercepts. Notice, if my vertex was here and this opened up, we would completely miss the x-axis. So very often, I like to plot the vertex and just figure out whether we're opening up or down, which is going to be completely determined by the sign of this number here, to know whether I should even bother looking for them. I can tell we're going to cross the x-axis here, so I will go ahead and look for those. If we're on the x-axis, that means our y value is 0. So I would simply set negative 2 times x plus 2 squared plus 4 equal to 0. Okay, now to solve this, I want to isolate the square. So I'm going to first of all subtract over that 4, so negative 2 times x plus 2 squared equals negative 4. Divide both sides by negative 2. X plus 2 squared equals 2. Take the square root of both sides. And be very careful. That is not x plus 2. That is the absolute value of x plus 2 that equals root 2. And to get rid of that absolute value, I want to recognize there are two numbers that have this number, since it's positive, as their absolute value. So x plus 2 could be either one of those, plus or minus root 2. Okay. Then to solve for x, I would subtract 2 from both sides. Now here, 2 and root 2 are not like terms. That's a root that I can't simplify, and that's an integer. So there's no way for me to combine them. I can just write them this way. X would be negative 2 plus or minus root 2. And so my x-intercepts, remember those are points, not numbers, would be negative 2 minus root 2, comma 0, and negative 2 plus root 2, comma 0. So now, if I want to graph those, I've sort of guesstimated where they are anyway, because I just drew freehand this parabola. If you are asked to graph something like this, I will ask you to make sure that you get these x values in between the correct integers. It kind of looks like this one's going to be in between negative 1 and 0. I'm going to want to know what integers that's in between. Now, if you have a calculator, you can just plug in and get a decimal approximation. But on exams and in-class quizzes, you will not have access to a calculator. So how do we do this? Well, notice that 1 squared would be 1. 2 squared would be 4. 2 is in between those numbers. Root 2 squared would give me 2. Okay, whatever number's under the radical, that's what I get when I square it. If that's in between 1 squared and 2 squared, that tells me that root 2 is in between 1 and 2. And I can figure that out without a calculator by just looking at what perfect squares it falls in between. So, when I look at negative 2 plus root 2, I know I've got to go more than 1 but less than 2 to the right. So 1 to the right would take me to negative 1. 2 to the right would take me to 0. We were correct that negative 2 plus root 2 is going to put me somewhere between negative 1 and 0. Now over here, I'm at negative 2. I've got to go more than 1, but less than 2 to the right. So if this was negative 2, this would be negative 3, negative 4. Negative 2 minus root 2 is going to be in between negative 3 and negative 4. Okay. So do make sure that you practice that. Now as you're doing the homework, I can't keep you from using a calculator. It's certainly fine to use a calculator to double check things, but make sure you know how to get to that level of accuracy without using a calculator.